Get into some protocols, some hardware, some things that may be a little bit more visual, easier to see what's actually happening with these things. We'll talk about switches, routers, and routing protocols. Switches and switching protocols. Switches do have protocols. We're going to talk about one, which is Ethernet. We're going to have some other ones when we go through this thing. We're going to talk about problems with complex layer 2 topologies. What if it is really complex? I had a friend in Roanoke who had helped, I don't know if he was the contractor or one of the subs, he did switches anyway, for a company in Chicago, a large company. And everything was working fine. And they decided not to use this protocol called spanning tree, which we're going to look at in a minute, which would avoid problems at layer 2. But they wanted redundancy, so they hooked some switches together. Well, they didn't create loops because we don't have any way to stop loops in layer 2. We've talked about that. He got a call one day, said the network's down. They flew him to Chicago, and when he got there, he said he walked into the NOC and moved one wire and fixed the problem. Somebody had moved a wire from one location to the other and created a switch loop. And when that happens without the spanning tree protocol, you get something like this one here. These are really dark here. I got this one is 192.168.1.3, and this one is 192.168.1.2. So they should be able to ping each other. We got switches here, layer 2 connectivity, no routers, no issues on the networks. When I go in here and I do this ping the 1.3, and we're waiting and waiting and waiting and waiting. We're waiting because we have created a layer 2 loop. We don't have a time to live. No TTL on this thing, so we need to do something if we want to have the physical backup, the physical connectivity, and we would like to have something like that because so that if one of these goes down, if this segment here goes down, then we still have a path to get from one location to the other. And that is, and don't worry about the configurations, I'm just going to enable the protocol. That will, and I'll enable it on all of them. You notice these amber lights here say that we're going through, we didn't talk about the negotiation process. And we're going to make all of them go through the negotiation process. It takes about a minute for this to happen. So they'll go through all this thing. We got one green one over here. They're going to determine elect a device that's going to be called a root bridge. And we're using the term bridge here with switches. Yep, and it is called a root bridge. And these lights may not all do what they're supposed to. Sometimes the graphics on this don't do what they really should do. So let's see if we can get there yet. And we're still looks like in the negotiating phase here. We don't have connectivity. We've got too many of them. There we go. Now we have one of them that's amber. And now we are working. So we can get from one to the other. We have physical connectivity, physical backup. One of these links goes down, this other one will automatically take over its position. What we do is elect, again, this thing called a root bridge, and once we get the root bridge, we find the least cost path to it, and each of the connections is going to have a cost based on the speed of the connection. So spanning tree protocol on switches allows us to have a physical loop without having the logical loop, the electrical loop that the information goes. And what my friend's company had done is they didn't use spanning tree. They had what I had before, but they had very carefully wired the network so that they didn't have one of these physical loops. Somebody moved a wire, created the physical loop, shut down the entire network. And if you shut down a company for a significant period of time, you can lose a lot of money. And if you or I do it as networkers, we probably might as well get our resume up to date when we do those things. So talk about those things. Switching protocols are used to prevent looping and congestion. Yep, we just did that. And VLANs can partition the layer 2 network. That's a term that's come up, I think, a couple of times, a virtual local area network. Not very hard to create when we do those things. So simple switch network. If we go like our simple switch at ECPI, maybe even the one that you have here, we had the NOC, the Network Operations Center, where we consolidated everything. And then we had a bunch of rooms out here. I had a switch that went from here to, I actually went to a layer 3 switch, which routed. And we had another room out here that went to a layer 3 switch, which routed. And here, we didn't have any of the redundancy because we didn't really have a situation that we needed the redundancy. We needed the communication to go one from the other, but we didn't have any of the physical links at layer 2, which will result in a failure. And it says here, redundant links could help. Now, redundant links are great, and if we have a failure, the other ones automatically take over. But at layer 2, the issue becomes based on kind of what we know is workstation A goes to workstation B, sends this packet in here, the frame doesn't know where B is, so it floods it out, all of the ports except the port it came in on. Comes to switch 3, floods it out, all the ports except the one it came in on. Comes to switch 4, floods it. So switch 2 now has gotten the MAC address of workstation A because it got recorded here in switch 1 in 2 places. It came in here, put it in its MAC address table, and it did great. Came in here, put it in the MAC address table on this port, and then it came in, it changed it to the other port. So what happens is we wind up with a broadcast storm in here. It just goes around and around and around. It has multiple paths, but it will crush the network, and that was what I was trying to show with the demo, that will crash the network when we do this. The Ethernet frame, we've looked at it before. The preamble, the 7 bytes, a series of 1s and 0s for synchronization, starter frame delimiter, destination MAC, source MAC, the type, the data, the CRC, the inter-frame gap, that's just an air gap between one frame and the next frame. There's no way to stop it. So we have to physically stop the connectivity of one of the ports, and that's what spanning tree does. It puts it in what's called a block state. It's not going to be sending data. It's going to be talking on everything else. We're going to communicate with these things. We had PDUs, protocol data units. Bridges have their own special protocols called BPDUs, bridge protocol data units, that will be used there. So spanning tree blocks ports to prevent loops, and this is kind of what we did. They have 3 here, they have 4 here. I had 3. That we're going to block as many ports as are necessary to create a loop-free topology in the network. So spanning tree protocol prevents a network shutdown, and it really does prevent network shutdowns, because if you have those things, you're going to have a problem. And this shows some other ones. I've got, let me see if I've got a one that's got more of them. You can see kind of what it does if you have a maybe bigger networks. No, it's not that one. I may have to look harder. Yeah, I'm gonna have to look. I've got one somewhere that has more that you can see that's got a topology something like the one that's up there. It's going to block all the ports that are necessary to prevent logical loops while still maintaining the physical loop. We have a failure, the protocol will automatically bring up the block port so that we can continue with the data transfers. The IEEE standard 802.1d operates in the data link layer, the layer 2 of the OSI model, prevents traffic loops, what again I was trying to show with the demo, calculates pass avoiding loops, artificially blocking links that were completing the loop, and we do call it blocking. STP is transmitted between the switches via BPDUs, bridge protocol data units. The 3 steps that it takes, it selects a root bridge based on the bridge ID, and I'm going to have a slide that shows you what the bridge ID is, and I don't think you need to know it for this, but how does it figure out how to elect this root bridge? And that's going to be the bridge ID, and it's going to be the lowest of everything. Examine all the paths between the network bridge and the root bridge, and it's going to find the most cost-efficient loop-free path to get there. Blocks links that are not part of the shortest path. The bridge ID is a bridge priority appended to, concatenated with, I think is the word with the MAC address. I guess the trick here is that all bridges by default have the same bridge ID, which is 32768, or the bridge priority, which means that we're going to use the MAC address to elect the root bridge. And the root bridge is then going to be probably the oldest device that you have. It's going to be the one with the lowest MAC address. The thing and the reason that this company I told you about didn't want to do spanning tree is because it does have a lot of traffic in it. Yeah, I was going to see if I had a spanning tree on Wireshark. They're not very big. The data is not very big, but it is very frequently. The BPDU, the bridge protocol data unit, is the way that they use to communicate with each other. It uses the bridge ID here, determines the root bridge, and then it does a loop-free path from every switch to the root bridge. This is just some that are in here. We got spanning tree for bridges. STP goes around and around, and again, not very big, 60 bytes captured with these things. The destination spanning tree for bridges is going to have its own address that it's going to go to. The source where it's coming from, LLC, a spanning tree protocol, the protocol BPDU flags, the root identifier is going to be the root bridge for these things, and then the bridge identifier. It is a protocol that is used on switches. It is enabled by default. If you don't want it, you have to turn it off. And it is one that, yep, you're going to see a lot of traffic, a lot of packets. They're not going to be very big. A lot of frames, actually. They're not going to be very big frames. BPDU, when we do the block port, and this is the cost here, the gigabit ports are going to be a cost of 4. The 100 meg ports are a cost of 10 maybe. So each speed is going to have its own, and as we get faster and faster, the costs obviously change. When we put 10 gig in, the cost is going to change again. Down there at the bottom, STP's job is to find all the links in the network and shut down any redundant ones, preventing the network loops from occurring. First, it elects the root bridge, and have all the ports forwarding will act, and that will have all the ports forwarding will act as a reference point for all the other ones. We elect a root bridge based on the election criteria, and the election criteria is going to be the lowest bridge ID. And if we don't change, and the bridge ID, or the first half of it, the ID portion, is configurable. But if we don't change it, the one that has the lowest MAC address is going to wind up getting elected for it. So it is one of these things, and the ports, the process, and I think these are in your book. But when we have a port, the disable there on the right hand table, disable means that we have shut it down administratively. We've turned it off. But the ports themselves, when they come up, they're initially in blocking state. And how long do they take? The one on the left shows blocking state 20 seconds. And then blocking state receives BPDUs. And then we go into listening state. And then the listening state for 15 seconds, it's going to build the topology. It's going to figure out if it needs to be blocked or not, basically, or stay in blocking state. Build the topology. Learning, it's going to be building a bridging table. It's going to be learning MAC addresses. And then after that, it goes into forwarding state. So when we turn one of these things on, it's going to take 50 seconds, 50 seconds, almost a minute for the port to come up. And that's when, on the packet tracer, that's when the lights were amber, was when it was going through the spanning tree process to determine which of the ports to block, to put in blocking state and to remain in blocking state. What if we need to have multiple links? What if we want to have a high-speed connectivity from one to the other? There are protocols that allow that to happen. Spanning tree stopped the loops. There are two protocols, and one of them is LACP down there on the bottom right, Link Aggregation Control Protocol, that will allow us to have this higher speed. And then when you might want to do that, you might have a particularly busy server that you, and now we can have what is link or NIC teaming, to where we can set something up to have NICs act as a single one. And what this does, what these protocols do, is allow, if I can get this thing up here, allow these devices, now we'll wait till they go through the spanning tree process. Well, I got one down here that already has been through the process. Allows these devices to aggregate all of these interfaces and say, hey, we're acting, and these are fast Ethernet 100, so that we're acting as a 300 megabit single connection, a virtual connection that goes from one to the other. So we don't have the situation that spanning tree is going to be blocking them. Otherwise, we're going to wind up with what's down here. I've got 4 of them connected to the switch, but only one of them is actually sending data from one to the other, trying to spread those out, but it's not going to work. If I configure LACP, or PAGP is the other protocol, then I can, and up here I've got 2 of them, and one of them is in blocking state. I can then have multiple connections, higher speed connections from my switches, or from the switches to the devices if they support the aggregation of NIC. So link aggregation, spanning tree blocks ports based upon physical links. Aggregation protocols allow us to have those multiple connections, the higher speed connections, and if one of them fails, it just lowers the speed of the connection. So the higher speeds are available from the aggregation protocols. In this case, the standard is LACP, Link Aggregation Control Protocol. Port-based VLANs, and VLANs are virtual local area networks. A virtual local area network says, I want to, instead of having physical networks, physical local area networks, I want to create them within a switch. Now let me see if I can get another little demo going here with this one. I have all sorts of those, and you're probably tired of them. VLAN. What we do with VLANs, and this has got, I think, one that works and one that doesn't work. I set it up in the Cisco class so that we go through what happens to these different things. But what we do is basically just go in and create a VLAN with a command that says VLAN, VLAN 1, VLAN 2, VLAN whatever, and then we can name it. Then we add ports to it. When we create VLANs, we create broadcast domains. Instead of having a situation like this one up here with the routers, where I have a network here, this is a 192.168.2 network and a 192.168.3 network, and I have to have a router between these things, I'm still going to have some sort of routing to go from one of these broadcast domains to the other broadcast domain, but there are techniques that allow us to do that. So what we wind up with are broadcast domains, and we can have them on the same switch, or we can have them on different switches. The commands really are very simple. We just create the VLAN and then we add the ports to the VLAN. What have we done? Let's see, the simulation. Let us go into here and see if we can ping the broadcast address. And this one is going to be, since it's a Class C, the broadcast is going to be 192.168.3.255. And since I've got it in simulation mode, I've got to tell it to go. So it goes into the switch, and then it goes out of the switch to all of the devices that are on that VLAN. You notice it didn't go to any of the blue ones. And then it goes to the green ones. It only goes to the green ones because those are the ones that are in that broadcast domain, that IP subnet. So we create broadcast domains with it. I was wondering why that, because I keep grabbing the wrong one. Now maybe let's do this one because it's a little bit better, and we can see if actually I don't know if this one's set up right. How's that? Ping 192.168.3.5 because oh, I've got it. It's not going anywhere because I've got it not in the VLAN. And that's one of the issues that you have as a configuration. This one is messed up. I use it in Cisco to go through step by step what happens with each of these things. But in a LAN, all the interfaces on the switch are in one broadcast domain. When we create a VLAN, we create broadcast domains. We create IP subnets. Broadcast domain, IP subnet. The host in the VLAN can be present in different physical segments. You saw that hopefully in the demo, in different physical segments, different switches. We have the ability to have a VLAN on multiple switches. The advantage there is you may have people in different physical locations that need to be on the same IP subnet, using the same server. We can have them in different buildings, different floors, different rooms, different wherever we want. In a teaching environment, you might have in a classroom, you have an instructor machine, and the instructor machine would be on the instructor VLAN so that it could get to the instructor resources, and the students would be on the student VLAN to get to the student resources. So with a simple configuration, we can create these virtual local area networks instead of having a whole bunch of different switches. Instead of coming into that room and having a switch for the instructor machine, I can have a port for the instructor machine, and then the student machines can be on all of the other ports to do that. We still do have to have, and it's not configured here, a router, a routing device of some sort in order to go from one of those to the other of those. And I was just seeing if, and those are not any of my Those are not any of my spanning trees that had other stuff in them. I was just looking to see. When a host in the VLAN transmits a broadcast packet, all the other hosts in the VLAN, but only in the VLAN, as you saw when I did that, only the ones in the green VLAN got the packets. The ones in the blue didn't. They were in a different broadcast domain, different IP subnet. Routers to transmit packets between the VLANs. Port assignments, and they say static and dynamic. If you do CCNA, talk about static, and static assignments are the one that I talked about. We create the VLANs and we add the ports. Dynamic is they automatically get added, but there's a lot more configuration and a lot more hardware that's required to do that. So we have those capabilities to do that. We have to configure the connection between these two switches. This connection here, and you notice it's a dash line. The dash lines are crossovers. A crossover like to like. All these are solid lines, straight throughs, unlike NIC to a switch, switch to switch crossover cable. But this has to be configured with what's called a trunk port. What we do is the switch knows which ports are on which VLAN. So when it sends data from VLAN, I think 3 is what this one would be, from VLAN 3 into the trunk port, it will then tag it, and it uses the 802.1q protocol to tag it. It says, hey, this came from VLAN 3. So when it goes through the trunk port, gets to the other side, the switch says, hey, this is supposed to go to VLAN 3. It takes the tag off because if it didn't, it's going to be a malformed frame and the computer won't recognize it. So it takes the tag off and puts it on the ports for VLAN 3. And then if we have the MAC address table up to date, it sends it directly there. If the broadcast goes to everywhere. If the VLAN 2, the blue VLAN does that same thing. The trunk port has traffic for all of the VLANs. The ports that the computers are on can only access the VLAN that they are assigned to. The trunk ports, all VLANs. The other ones, the access ports, and those are called access ports because they access the switch. The access ports can only be on a single VLAN, the one that they're assigned to, and they can communicate with all of their other friends that are in that same VLAN. VLAN ID is added to the Ethernet frame headers to transmit to the correct VLANs, and the process is called VLAN tagging. So we tag these things. There are 2 protocols. There used to be 2 protocols. Everybody keeps still talking about ISL, the one down there, and with all of the colors on it, the Inter Switch Link header structure. ISL was a Cisco proprietary VLAN protocol that hadn't been used in probably 10 years. The one at the top there is 802.1q, which is the standard, and it's the one that is currently used. It's used by Cisco, used by others, so that we can have different vendors. We can tag the frames for each of those. The default and a couple of things here. The default VLAN is VLAN 1. It's created by default. Well, I call it the default VLAN, and by default, with the default VLAN, all of the devices or all of the ports. Let me see if I can drag one up here, and we will look at it. All of the ports are on VLAN 1, the default VLAN. The other term there is native VLAN. A native VLAN is the one that doesn't have tag frames. It's for backward compatibility. If we have a hub, for instance, coming into a system, it doesn't know anything about tagging, so its frames are going to be untagged, and those are going to be on this thing called the native VLAN. But the VLAN 1, when I started the switch, brand new switch, drug it up there, would be with all of the default configurations. the ones that are created for us, VLAN 1, named the default VLAN, and all of the ports are on it. These others down here are created, but they're not used anymore. They really do just kind of get in the way when you want to do other things. So we have the default VLAN and the native VLAN. VTP, the VLAN trunking protocol, is a configuration that allows us to, if we have 50 switches in our network and we want to add a VLAN. Well, you probably don't want to go to 50 switches and type VLAN 300, name new VLAN or whatever it is. What VTP allows to happen is that we create it on a single switch and then it gets sent to all the other switches. And that's why consistent VLANs on the switches. We create it once, it gets sent to and updates all of the other switches using the VLAN trunking protocol, VTP. Switch management. Let me see where we are here. Yeah, we only got a couple. I want to go ahead and finish the switches and then we'll take a break and then we'll do routers and then we'll do labs. Switch management, we talk about in-band and out-of-band access. And I had one that I think that I wanted to try to do. And I forgot what I named it. Anyhow, the in-band is within the network itself, where we would telnet or SSH. Telnet, port 23, SSH, port 22, where we go from one to the other. And the reason that I wanted to do that is kind of to see the terms here for it, the in-band and the out-of-band. What we do with these things, I think, is to set up. And you can see I've got spanning tree here, so we're going to have to wait till it gets ready. If I want to manage, and I've got this one set up for remote access, it's got to be configured for these things. So I have to stall here for a minute until my spanning tree gets through checking for loops in the switches. And of course there aren't any in these because they're all separated by the switches themselves. Well, we can go ahead and do the in-band. The in-band was when we would take an RS-232, and you heard that term, a serial port, and connect it to either the aux port, the console port is where we're going to go. The auxiliary port there, the aux port is designed to allow you to connect a modem so that you can have out-of-band management remotely. One of the things, let's say that you're in wherever, let's say you're in New York and you have a router in Los Angeles and you make a mistake, you do an IP configuration on the interface that you telnetted to or SSH to and hit the enter key, and all of a sudden you don't have connectivity anymore. The out-of-band would allow us to then connect to it via the modem and make the changes that we have to. This one would be local. This goes to the console port. This would be physically within the device itself. We have to go to a terminal, and then when we go to enter here, I am now on the router. So I have accessed the router here locally out of band. I'm not using what we call the in-band or the telnet or the SSH. The in-band, let me see what it is, 3.2, I have to get the IP address. The in-band would be if I would use telnet, and this is not set up for SSH, it's not configured. So if I telnet 192.168.3.2, it asks me for a password, and you have to have a password configured for this thing. And now I am on the router, in another router, and I can do the configuration. So inbound, out of band, in-band, telnet, using the IP IP structure in order to do those things. Out of band access from the outside. things that we can configure on the switch, the VLAN, the speed and duplex. If we want to do manual speed and duplex, they are configured for auto detect, auto config. No reason to not do that. Trunking, spanning tree protocols. We saw spanning tree, turn it on, actually I turned it on, it was already turned off. Port binding or port aggregation for these things, when we bind or aggregate the ports together to give a higher speed, and we then don't shut down the ports using the spanning tree protocol. The port mirrors when we want to maybe do a sniff or a protocol analyzer that we want to watch traffic on another port, because remember, in a switch you only see the traffic that's to you and the broadcast traffic. If I want to monitor the other traffic, I have to port mirror. I have to be able to copy the frames from the port that I want to see into my port where my protocol analyzer is running. So that's what that one is. We can do quality of service. Quality of service, voice phones, VoIP phones that we plug into the switch. We're probably going to give them, we are going to give them a higher priority than the data, because voice, with any disruption in the data flow, gets to be pretty erratic. Data, we don't really care if it's delayed a little bit. We don't want it to be forever, but if it's delayed, a nanosecond or a microsecond or a millisecond, it's not going to make a whole lot of difference. That will make a difference in a phone system. 802.1x is a secure access. What it actually requires is that you log in before you can get an IP address, simply put, and then secure the switch using the SSH protocol, or we use filters, access control lists in order to control who can get from one to the other. Power over Ethernet is a way to send power to the devices over the Ethernet cable. It's just what it says. Why would you want to do that? A lot of times you put things like the wireless access points or the wireless routers, you put them in an overhead somewhere that they don't have any power. IP phones may take their power from the voice over IP, because you don't have a plug. When they designed buildings, they didn't design them to have a plug for the phones. So they need power. So we might have those. The IP cameras, the remote cameras that you put in the parking lot or put in the hallway or put in the rooms that you're monitoring with, you don't have the real ability to plug them in. So we use the voice over IP or voice over IP, power over Ethernet, in order to send the power to those devices. PoE, the IEEE standards 802.3AF, and different amounts of power depending on the devices themselves. The 15.4 watts for standard devices and 25 watts for the newer devices using the newer standard. And you might say, well, what if I plug in a non-power over Ethernet device into a power over Ethernet port? And I always wondered that. It checks. It sends a little signal out to be sure that what's plugged in is a device, a PD down here, a powered device, the power sourcing equipment, the switch, the power Ethernet switch checks to be sure that it is a powered device, that it needs power before it sends power over the Ethernet cable. But it's a way to kind of minimize what goes on. The other thing that you need to consider if you're using these is these PoE switches are probably going to take more power than a standard switch, because they've got to provide power to the devices. These are just if you don't have a PoE, a power over Ethernet switch, you can get adapters that will allow you to send the power over the Ethernet. Requires the power servicing equipment device first determine whether the node is capable, and if we don't have a PoE, you can add the PoE adapters, and that's what they look like down there at the bottom. The adapters that we add power to them using it. So let's do the assessment questions here and then take a break. What limitation of the spanning tree family do protocols like SPB and Trill try to overcome? and I wasn't paying attention. Are those the answers? Anybody? Somebody? Okay, so Dana said, yeah, D is his answer, and that is the correct answer. And that's what we're talking about with switches, is the multiple paths. What happens to a non-tagged frame on a VLAN trunk? Go with C. It goes to the native VLAN. The native VLAN is the untagged VLAN. And that's for backward compatibility. Although I guess people are still using hubs. The only time that we ever really used a hub was when we wanted to see. We didn't do a port mirror. We didn't even think about the port mirror. We just stuck a hub in to monitor all the traffic when we were looking for something that we didn't know where it was coming from. You're using LACP, and I did not go through the configuration, and they didn't go through the configuration. I can. You're just setting up all the ports. Which combination will lead to a successful auto negotiation? An active-active and an active-passive will do that. Passive-active. If you have active and passive together here, you got active-active is going to active-passive will, and passive-active. Two passives will not create an aggregated, an ether channel is what it's called. Won't create an ether channel, a grouping of the ports. A switch you're considering purchasing is marked as a smart switch. What kind of interface do you expect to have? Choose the best answer. And I'll go with a web-based. You were distracted while configuring a switch, and now there's a constant congestion from an overwhelming amount of traffic. Think broadcast storm. As you go back through the settings you have modified, which can you likely rule out as a cause of the problem? I'll tell you, I don't like any of their switch questions for CCNA. Yeah, but for here, not so sure. I'll have to look at the objectives again. And they want to hear the B, the MTU, the maximum transfer unit, and power over Ethernet. LACP, if we have it configured wrong, and as long as we've got spanning tree configured here, we're probably not going to have a really big issue, because it's going to shut down that and stop all of that link traffic. The VLANs are going to break up the broadcast traffic, obviously. If we don't get the LACP bundled, the other ones will just go into standard spanning tree configuration and get blocked when we do that. So I think that's the last one of those. Talk about routing after we take a break. Let's come back at about, let's come back at 1/4 the hour. I know it's a little short, but I want to get this done and get you into labs. Let's go ahead and get into the routing. I think and talk about routing tables, routing process, common routing protocols, and then network address translation. I think what I want to do is to look at some of what they're going to talk about in the slides first. The first thing, and this is the same one that we used a little earlier. This one up here doesn't really have anything configured on it. If you're actually connecting from one to the other, you gotta go using this. The simulator here has this cool little thing called a CLI, the command line interface, which allows me to not use that. If I want to see the routes, I use in Cisco the show IP route. And the first thing they're going to talk about is local routes. Local routes are the networks that are directly connected to the router. Whenever these things start out, these router things start out, the only thing that they know about is what's there, what they can reach out and touch, what's connected to them, what addresses is on them. So I've got the 192.168.108, 195.168.1 and 195.168.2 are directly connected to these things. And the C here says that it's connected. L is local, and if you look at the CIDR notation here, 32 bits says that's an IP address, 192.168.108.2. 24 Class C network address for this thing. So the first thing they talk about is local routes. Local routes are the things that are directly connected. The other is we can have a default route. And the default route says, hey, if you can't figure out what to do with this thing, send it here. So in order to configure that, it would be IP route, and it is 0.0.0.0 with a subnet mask of 0.0.0.0. So, and then we're going to have the next hop, which is going to be 192.168.108.1. So now if I do a show IP route, I have this thing up here. It's called the gateway of last resort to network, and that's to network any network that it can't find a place to go, it's going to send it here. So we have those things. The next thing down here has got an S, a static with a star, which says it's going to be a default route. Then they talk about common routing protocols. The routing protocols that you're going to be exposed to, I guess, are going to be RIP, EIGRP, and OSPF. Yeah, there's a lot of just letters. RIP is Routing Internet Protocol, and that's the one that they talk about here. It's the simplest one. OSPF, EIGRP require a little bit more configuration, a little bit higher powered resources. RIP is okay for small networks. It uses hop count. Hop count, how many routers can we go down the line? And its maximum hop count is 15, so it's going to be relatively small network. So you can't go more than 15 routers. I'm going to go ahead and configure it here just to go through to see that the config T gets me to configuration mode, and I just do router RIP. And then I advertise the networks that are directly attached to me. 192.168.108.0. RIP is a class full, so I don't have to put the subnet mask on it. It's a class full network, so it uses whatever the class is. And then we do network 195.168.1.0 and then .2.0. Now then, if I did it right, if I do a show IP route, I got a whole bunch more routes. I know how to get to all these other routers. And what happens is, using broadcasts, each router shares its information with its neighbor. So when I am doing this router says, hey, I know how to get to the 1, 2, and the 108. So to get to the 1, the 2, and the 108. And this guy said, I already know how to get to 108. Don't bother me. So what we do is say, hey, to get to 195.168.1, go to here. And then I'm going to add 1 to the hop count. He is then going to tell all of his neighbors about his directly connected networks and the ones that the neighbors have told him about. And they share these things. RIP uses a broadcast every 30 seconds. Which means that, this thing could be flow to converge. Convergence is when all of the routers know about everything. If this network goes down up here, the 2 network goes down, then he tells it that the 2's network down, 30 seconds. 30 seconds later, network is down. 30 seconds later, the network's down. So we're taking a minute and a half before this guy over here finds out that this network went down. Slow to converge, very simple, hopefully, as you saw, to configure. It's a very basic one. Even Windows still has it, I think. A Windows Server, you can put a Windows Server into a RIP network. So the IP routes themselves, let's go back and look at one of those and see the elements of an IP route. Show IP route. Got to spell route right. So we have the destination network and the IP address. Then we're going to have this thing called the administrative distance, which is how reliable it is and how far away is it. It says that this network is 1 hop away. And how do I get there? I get there using 192.168.3.1, and to get to 192.168.3.1, I go out gigabit interface, gigabit Ethernet 0.1. If we go on down, some of them have, down here, this one's got 2 options. We can go out either 3.1 or 5.1. These are each 2 hops away, equal cost. And they'll actually share, they'll send half of the data out 3.1 and half of the data out 5.1, but at equal cost. But we still have the same information here, the destination network address with the subnet mask, how far away it is, what's the next hop, the IP address of the next router, and what interface do we go out of to get there. Their route tables, the reason I did this, the route tables that they have in the book and I put in the slides are kind of indicative about what they are. But the table, we have the network address, the mask, the gateway, the next hop address, the interface that it goes out, and the metric. The metric, what is the cost to get there when we do those things. The local entries we looked at with the local entries are the ones that are directly connected to it before we share them. The local ones. The ones that it knows about. The ones that it can tell all of its buddies about. The remotes are going to be someplace else. This is viewing a routing table and exercise here. This is why I said that I wanted to look at what a route table looks like. That's what a Cisco route table looks like. They all look very similar when we do these things. We have remote routes, static versus dynamic routing. Dynamic routing was the protocol, the RIP, when we configured it, is a dynamic route, dynamic routing protocol. The static was the default route that I put in where I type it in. We also have interior and exterior protocols. The interior protocols are the RIP, the OSPF, and the EIGRP. Just trust me on the letters. And then there's one called IS-IS, IS-IS, the ones that are in the table over here on the right. We have a single exterior protocol. Interior protocols are the ones that we use inside of our enterprise networks. Exterior protocols are the ones that the ISPs use to share routes with other ISPs. Exterior routing protocols are what the internet runs on. And the only exterior protocol is BGP, Border Gateway Protocol. Is the only one that's there. We can have multiple protocols running on the single router. If we needed to have RIP and EIGRP running, we could do that. We have distance vector and link state protocols. Distance vector is RIP. It goes in a direction for a certain number of hops. A link state of the links is what they always talk about. They have topology tables, and they will determine for themselves what the best routes are. And if you want to see the routes that are on your computer, go to the command prompt and type route print. The computers themselves have routes on them, and that kind of makes sense of how that they would have to. And if you don't want to, I will try to do that for us. And if I do a route print, I get a whole bunch of routes, IPv4 and IPv6 routes. But the 0.0.0, hey, the default route goes to the gateway, the default gateway. The interface that it goes out of is 192.168.1.27, which is the IP address of this computer. The 127, where does it go? 127, 169.254 on link. 169.254, remember, is going to be the APIPA address. The 192.168.1 network, where does it go? It goes out the interface. It goes onto the network via the interface. Same sorts of things that you saw in the Cisco route table is in the Windows route table also. But anyhow, distance vectors, arrays of distance. We go a certain number of hops, communicate with the neighbors. They use a broadcast. They broadcast, and broadcasts go as far as a router, so they broadcast with each other. Distance vector, the distance vector protocol is RIP, and it has a hop count limit of 15. If you get a hop count of 16, that becomes infinity. Link state protocols, more resources. They build a topology table of the entire network, and they do their own calculations using their own algorithms to determine the best route to get from one location to the other location. EIGRP, which keeps showing up as a Cisco proprietary one, is called a hybrid protocol, and it's supposed to take the best of each one. These things, and this is the get from one to the other. So yes, I have your update added network 1 and 2 to my routing table. So this guy down here got network 1. He tells B about network 1. He adds it and adds 1. See the hop count here is 0 because it's directly connected. He adds 1 to the hop count. He then tells C about it. C adds 1 and adds 1 to the hop count. So it says that the one network is 2 hops away. So as they get these things, and we use this thing called a split horizon. And the split horizon says that I told you about 1, you can't send that information back to me. And that might be, 1 goes down. So A tells B that 1's down. So I don't know how to get there. C says, hey, I know how to get there, and it sends it the update. So now I've got bad data. So in order to prevent that, we use this split horizon. Split horizon says that you can't send that information back. And that's what this one down here is saying, that sending info about C router to A router from B router, and then sending info about C router to B router from A router. Since B router sent it, it can't send it back to B. Split horizon does that. RIP also has a whole bunch of timers to prevent routing loops whenever something goes down or something happens in the system itself. Autonomous systems are used by BGP, the Border Gateway Protocol. And these autonomous systems are numbers that are assigned by IANA, which is the Internet Numbers organization. And they use them in order to communicate with other autonomous systems. And they talk about here a transit autonomous system connects to multiple other networks, serves as an open conduit for traffic, multi-home to multiple other networks, and a stub is always going to be 1 at the end. So if we have, my house would be a stub route, your house would be a stub route. We have all of this stuff out here going from one to the other to the other. If I have one stuck down here by itself, it doesn't go anyplace else, and these keep going. It doesn't go anyplace else, it's going to be a stub. So a stub autonomous system only connects to one other autonomous system, so no other networks will appear to be just part of the upstream autonomous system. Got an image here of what are we talking about. We have an autonomous system number, and this is what a BGP might look like. And when you configure it, you have to tell it what the address that it's connected to, as well as the autonomous system, so that they remote autonomous systems update each other's route tables. And eventually, by doing that, autonomous system to autonomous system to autonomous system, they build route tables, huge route tables of the internet. And that's why, and if you think about when we talked about IP routing, why do we want to group these IP routes so that we can do aggregation, these IP networks, so that instead of having 15 or 20 or 30 of them with a 24-bit mask, I can have one with a 16-bit mask, as long as I've got them assigned correctly, grouped correctly, so that we can send them as a group, or specify to send them as a group when we do those things. But autonomous system numbers are assigned by IANA, are used by the exterior border gateway protocol, the exterior gateway protocol. A couple of other things about routers. This is called first hop redundancy. First hop is going to be your default gateway. What this first hop redundancy does is creates a virtual router here, and we have two physical routers connected to it. One of them is going to be the active router, and the other one's a standby router. If something happens to the active router, the virtual router keeps track of what's going on and says, "Up, it's down, something's happened." It then starts sending the traffic to the standby router. The standby router will take over, so we don't lose any connectivity. The problem here is you've got one guy just sitting here, one standby router just sitting here waiting for the active router to fail. So, you know, you can configure, we won't go into that. If you do Cisco, we'll configure it twice so that we can use both of them at the same time. But standby router to continue connectivity out of our network. First hop redundancy, first hop is the default gateway that we use in our networks. The next thing, and this is the last topic I think in this one, is network address translation. And we're going to have three kinds of network address translation. We're going to have a static translation, which is a one-to-one. We're going to have a pool, a dynamic, and then we're going to have one called port address translation. Port address translation is what you and I use. We have a single IP address, and we talked earlier tonight about ports, and port and an IP address created a socket. So I have a whole bunch of ports, so I can create a whole bunch of sockets on my outside NIC. So I can use my private addresses inside and either NAT, network address translation, NAT them to a public address to go onto the internet, or I can use PAT, just use a single IP address and a whole bunch of different ports to create sockets in order to do that. Or I may have a range of IP addresses and I will put them in a pool and dynamically assign them. And that's what this is showing. The process to configure it obviously a little bit more complex than that, but on this one we go through the NAT router and we go from the 192, and I wish they had used a public address over here, but they didn't. But 192.168.10.100 gets NATed to 10.20.0.25 in the NAT table. So these two, one side or the other, when it comes back in, looks in the NAT table and says, "Oh, this came from this address, send it to this private address." Why would you want to do that? If I had a public address out here, let's say I had a web server on my private network. The web server had a 192.168.5.3 address. I might NAT a public address to my private address so that users would come to the public address on my NAT router, my NAT device. It can be a router or a firewall. And then when they come to this public address, they get automatically sent to my web server. And not only that, I would say public port 80, and I would only allow port 80 and maybe 443 if we had secure through this thing. So we have a static NAT, which is always going to be the same. It's going to be a one-to-one network address translation to do those things. When I do this, here are the other NAT methods, a one-to-one, the NAT table, a one-to-many. In this case, I have what I have one-to-many, the 192s here, one-to-many addresses, the 101, 102, and 103. I would have a pool of one-to-many is going to be pat, but we can have the one-to-one, the statics, or we can have a pool of addresses that are dynamically assigned to it, or we can have the port address translation, and that's what this one, the source NAT, destination NAT. Yeah, I got ahead of myself. Source NAT is when we're going out of the network. We NAT the source that goes from one to the other. Obviously, the NAT table. The destination NAT, we had the internal server here, and that's what they have. That we go to the 10.11. It goes to the 101. Goes from what would be a public address. A public address on the internet will then get natted. Your queries will get sent to our router inside our server inside of the network. These guys use private IP addresses, get natted to public addresses, and that's why I wish that they had used something other than 10, because we're going from a private to a private. We're really going to a private to a public so that we can have our queries routed on the internet. Private IP addresses are not routable on the internet. They're routable addresses privately internally, but not in the public internet to do those things. So a source NAT is when we NAT the source IP address to a public IP address so that we can get out. A destination NAT is when we NAT a public address to our private address so that they can get to the resources inside our private network, our protected network. And most people aren't going to do that because you don't want strangers coming into your protected network, but it is something that's possible. The last process, and this is the one-to-many, is a port address translation, a PAT. And what's going to happen there is these guys will have and you saw when we looked at them, we had a 192.168.100.101, and it had a source port. And ports are usually written with a colon, so port 53,000. And it may be natted to 10.10.10.11 port. Now let's say 12, or no, let's do a high number. Let's do 60,000. Yeah, let's do high. Let's do 40,000. And then the next one might be on 53,001, and we would NAT it to 40,001. What we're doing is creating sockets so that we can keep track of the connections. And this guy with this public address would go to the internet, to the web page that we're going to, get the information and come back and then look in the NAT table and say, hey, port 40,000, that's supposed to go to port 53,000, 192, 168, 100, port 53,000. So it'll send that to this IP address and send it back. What this allows us to do is to have a limited number of IP addresses that we use publicly by using port address translation and creating sockets, socket, IP address, and a port number to do those things. That is an overview, I guess, of routing. We have the assessment questions here. Your company's network is too big to use static routing, but the topology is simple and doesn't change very often. What routing protocol would be the easiest to use while still meeting your needs? Choose the best response. Which is the small? We've got a D here, RIP, Routing Internet Protocol, small network, 15 hop limit on it. And don't change a whole lot. Remember, it takes 30 seconds for each of those things to be promulgated. It's a broadcast the updates of the entire entire routing table, topology table, entire routing table every 30 seconds. Your company network is a multi-homed autonomous system. what protocol would your gateway routers need to learn internet paths? So which one of them had autonomous systems? Good, BGP for that one. Even with modern routing protocols, you still might want to set static route entries. True or false? We'll go with a true on that one. If nothing else, the default route, because if it can't find anything, send it to the next router. Maybe it can. It can do that. Because the next router may have a static route to the place that you're trying to go to. What might a router using PAT change on packets passing through? And this one kind of goes crazy. It's got 3 answers to it. So what might it change? It's either a source or a destination NAT. Anybody want to try? AC and F. The destination port for the incoming packets, the destination address, and the source port for the outgoing packets when we do those things. So we talked about switches, switching loops, spanning tree, how to prevent the switching loops, the switching protocols that we use. We talked about VLANs with the switches, a number of things that we can do with switches, in-band and out-of-band management of the switches, and then routers. We looked at routing tables, the routing protocols a little bit, RIP specifically the routing protocol, common routing protocols, network address translation, how it kind of works, how we had the first hop redundancy that we looked at, the first hop redundancy protocol, autonomous systems, the how route tables get updated, what route tables look like, the information that's in the routing tables. So I will